In this paper, we studied a number of running buffers for the tabletop object rearrangement problem. This is a joint work with my colleagues Siwei, Feng, and my advisor Jingjin. In the rearrangement problem, a robot arm moves object from a start arrangement to a goal arrangement. When we use overhand grasps to move objects around, the constraints of the movements comes only from the positions of the start and goal poses. This problem finds many applications in home automation and industrial automation. Minimizing the number of pick-and-place operations directly lead to the increase of the system throughput. We represent the constraints with a dependency graph so that this rearrangement problem can be transformed into a graph layout problem. But in many cases, the dependency graph forms a cycle. To solve the cyclic dependency, we need to break the cycle, which require a temporary location for storing an object. We call the temporary location a buffer, which may be internal or external. We work with external buffers in this study. In large-scale problems, the buffer locations can be reused multiple times to break cycles one by one. In this animation, the translucent disk is used to imitate the motion of the end effector. In this example, we need to put at least 3 objects into the buffers, but we only need one buffer location and reuse this buffer location 3 times. That is why we call the external buffers the running buffers. Specifically, the size of the running buffers is the maximum number of objects stored at the buffer at any moment. In our paper, we find the rearrangement plan to minimize the size of the running buffers. We first show the optimal rearrangement plan of a labeled instance. The minimum running buffer size of this instance is 2. The linear vertex ordering is the ordering that the objects leave the start poses in. And we also show the change of the dependency graph as the plan gets executed. First of all, object 5 is moved to the buffer. Then object 6 is moved to the goal. A goal pose is collision-free when all its dependencies are inactive. For the unlabeled case, the goal positions are interchangeable. In this case, the dependency graph is a bipartite undirected graph. Like the labeled case, the rearrangement plans can be represented by a linear ordering of the start vertices. An object from the start pose will move to the buffer only when there's no available goal pose. For the unlabeled disk scenario, through careful constructions and analysis, we proved that the running buffer size is lower bounded by omega square root of n. And we also provide an algorithm that delivers a matching upper bound. For the labeled case, we proved that it is hard to even compute an absolute approximation for the running buffer problem. Through the dependency graph abstraction, we propose algorithms that finds the optimal rearrangement plans. We have an exact algorithm, DFDP, to minimize the running buffer size. It is based on depth-first search and can solve the running buffer problem very efficiently. To conclude, in this paper, we proposed a running buffer problem in a tabletop rearrangement setup. And we also proposed a graph representation for the unlabeled case. Based on the dependency graph structure, we proved important structural properties of the problems and designed several exact algorithms for computing the optimal rearrangement plans, minimizing the number of running buffers. For future work, we plan to take a look at the hardness result of the disk scenario. In this case, the dependency graph has a bounded degree. Besides that, for the labeled problem, the lower bound is omega square root of n, while the upper bound is still big O of n, so we will also try to shrink the gaps of the bounds in this problem.